It's been almost a century since the invention of the jet engine. When Sir Frank Whittle first strapped a gas turbine to an airplane, few could have predicted the revolution about to unfold. Within 50 short years, global trips, which one would have taken months, were now finished in a matter of hours. The world had shrunk. Formerly impassable terrain flitted by below the windows of commercial airliners. But in the long decades since, advancements have stalled. While jet engines have incrementally improved, producing faster, more fuel-efficient planes, nothing has been as groundbreaking as the engine itself. That was until China revealed a new plasma jet engine. Though the concept isn't new, the design offers the tremendous opportunities for both atmospheric and space-based travel, maybe even a spaceplane. In this video, I'll explain the potentially revolutionary technology and answer whether it's truly the future of air travel. Welcome back to our channel. If you haven't already, make sure to hit that subscribe button and ring the bell so that you get notified every time we upload a new video. As the jet engine took off, everyone began darting around the globe in droves. Air travel has become the norm. Yet, with this explosion in air travel, we've seen aviation emissions quadruple since 1966 and double since 1987. In 2018, globally 1.04 billion tons of CO2 were spewed into the atmosphere from aviation, or roughly 2.5% of all CO2 emissions. That's hardly surprising. The average plane guzzles 36,000 gallons of fuel over a 10-hour flight. With ever more people demanding access to rapid air travel, it's becoming a serious problem. But how do we simultaneously reduce aviation fossil fuel use and increase flight capacity? The answer may be the plasma propulsion engine. So, what exactly is it? Traditionally, plasma-based thrusters are used in spacecraft propulsion. These thrusters are perfect for altitude and precision control, particularly during low-thrust maneuvers. They're also the simplest form of electric spacecraft propulsion. That's not a bad thing, however. Plasma jet engines are remarkably successful. There's no need for high-voltage grids or complex anodes or cathodes to accelerate charged particles in the plasma source. Rather, the engine propels the spacecraft forwards by passing a high-current electric arc through the fuel source. That then generates heat, turning the fuel into a plasma, a supremely hot state of matter. Using two electrodes, the plasma is then accelerated from the exhaust at high velocity. Think about when you rub a comb on your head and can repel a balloon. It's the same principle dialed up to 11. The plasma ejection then begins to move the craft forwards. In reality, the acceleration is minimal, but in the dark vacuum of space, there's little to no friction. So any amount of constant thrust eventually reaches extremes of velocity. You'll find these complex plasma jet engines on prominent space missions, including for the European Space Agency, the Iranian Space Agency, and of course, NASA. Indeed, the NASA Dawn space probe is kitted out with the latest plasma jet engines available. Tampering with plasma, the same state of matter found in the scorching sun, is a dangerous process. But there's a key benefit. The propellant can be almost anything, including argon, carbon dioxide, even human urine has been suggested. Yuck! Nor do you need any fancy high-voltage grids or anodes and cathodes to accelerate the charged particles in the plasma. Instead, the higher current electric arc supplies the currents and potentials internally. Confused yet? Don't be. The plasma jet engine is like the electric engine to the combustion engine. It still powers the car, or in this case, spacecraft, just with far fewer moving parts. There are a few drawbacks, however. First, the power requirements are astronomical. The Vasmer engine demands 200 kilowatts of electrical power to produce 1.12 pounds of thrust. To meet such energy demands, you'll likely need a fission nuclear reactor. That's possible, but it does add substantial weight to the craft. More weight means more power is needed to launch, which in turn further ramps up the power needed in a vicious cycle. Second, the scorching plasma erodes its confines, eventually damaging the thruster cavity and support structure, leading to system failure. Still, the stats are astounding. The Vasmer engine, being developed by Ad Astra Rocket Company, could reduce the travel time from Earth to Jupiter from 6 years to 14 months, and from Earth to Mars from 6 months to 39 days. In short, it turns space travel into a very real possibility. Yet the prospects for revolutionizing air travel remained distant. That was until Chinese engineers revealed a working microwave thruster prototype in October of 2021. While prior engines struggled in Earth's atmosphere as ions generated from noble gas pollutants tend to lose thrust due to air friction, the new design uses only air and electricity. The researchers at the Institute of Technical Sciences in Wuhan demonstrated an impressive thrust level from the tweaked design. Indeed, the concept draws upon the design of the combustion engine. Ionized air is used to produce a low-temperature plasma. That plasma is then fed into a tube using an air compressor. After being bombarded by microwaves, the ions in the plasma shake violently, impacting other non-ionized atoms. The temperature and pressure rise rapidly, generating higher and higher amounts of thrust further down the tube. Already, the design is rivaling low-end jet engine technology. It's been reported that the Chinese plasma jet engine pumps out a propulsive force at 400-watt electric input at 6.29 pounds of thrust, 28 Newton per kilowatt. For comparison, the cancelled Airbus E-Fan two-seater electric aircraft with a pair of 30-kilowatt electric duct fans produces 1.5 kilonewtons or 5.62 pounds, 25 Newton per kilowatt. Still, a modern commercial Airbus A320's engines power out 220,000 newtons of thrust combined. So, for the new plasma jet engine to replace this jet engine, it'd need 7,800 kilowatts of power, roughly equivalent to 570 Tesla Powerwall 2 units, for just 1 hour's flight. Considering an Airbus A320 can only carry a third of the required power walls, the new engine is unlikely to be jetting off anytime soon. Nor are the public likely to get behind nuclear reactors strapped to jet planes, even if they save a few hours when traveling from Hong Kong to New York. The Chinese researchers may have made substantial progress, but for now, plasma jet engines are unlikely to take over from their predecessor anytime soon. But what do you think? Are electric plasma jet engines a fancy solution to an unnecessary problem, or do you think the technology has wings to fly? Let us know in the comments below.